Hi, Ghislaine. How are you? You can check out your notes. And today we're going to talk about cryptography in Python. So let me log into my Ubuntu. Okay. Okay. Good that you're okay. Hope you had a good weekend. All right. So this is the last chapter in the book. And we're going to touch on how to work with cryptography in Python. There are various modules, I think, in the prior class and also before we talked about using cryptography as a module, but we're going to look into other modules in this particular chapter, okay? Also, we're going to go over the assignment today. So if you want to take a look at that, there are only 10 questions. So to begin, we are going to define cryptography. So it's a way that we can change plain text to unreadable text. And cryptography is used in a lot of areas, from secure web to authentication to digital signature. So now, a little different than the general cryptography, hash functions, as you know, is a one-way encryption. It allows us to generate a fixed length hash value for a certain plain text input. So if we're looking at a type of plain text or even a file, we can generate a hash using the hash function. Now, key hash function is a way that we can build MAC or message authentication code. This is going to allow us to prevent brute force attacks. So to break down encryption, there are two types of encryption. There's symmetric keys and asymmetric key or public key infrastructure. And under each category, you will have different algorithms. So symmetric key is when we would use one key to decrypt and encrypt and decrypt. So we can use the same key. And when we do that, we would share the key or send the key from the sender to the recipient. So that way the sender can encrypt and the recipient can decrypt. Public key infrastructure or asymmetric key uses two different keys. One is to use to encrypt, usually that is a public key, and the private key is then used to decrypt. The example of PKI or asymmetric would be digital signature or RSA. Now, going back to the assignment, we, number one, can define the two areas of cryptography, hash function and key. I have a typo here, hash function. So a hash function is a one-way encryption, as you've seen in the notes on page 1. This is going to allow us to output a fixed length hash value for a certain plain text input. It is also used to recover the content of the plain text. Now, the only way that the input data from the hash code is brute force, I have a typo here, by using search is that they would use a matching hash from the table. So if the hash is matched, then by retrieving from a hash table, then brute force can be possible. Otherwise, it would not be possible. Your key hash function is a way that we can build message authentication codes. It is used to prevent brute force attacks. So we can define these two, and they are different in that the hash function generate the hash value and key hash functions is used for MAC. Now, the intention, the goal for both of these are going to be reducing the brute force attacks in general, but the hash function generate the hash value. So for 2, we want to describe the difference between symmetric and asymmetric or PKI algorithms. So we say that symmetric use the same key to encrypt and decrypt, where PKI or public key algorithm use 2 different keys. One is to encrypt and the other is to decrypt. The example for symmetric, you can also find this online. I didn't include all of them in the notes, but you often find AES under symmetric, and that stands for Advanced Encryption Standard, or DES, which is Data Encryption Standard. That's the old technology. Triple DES is the later technology, and that is just going through and encrypt it 3 times or generate multiple keys to encrypt. And that same key would then use to decrypt at each level. For the PKI or the public key algorithm, we would use 2 different keys, one to encrypt and the other to decrypt. And the example for this is digital signature, often use PKI. RSA is also very common, and RSA is often used in authentication, as you know, in Raspberry Pi, in Linux systems, when we connect to a device via terminal, Diffie-Hellman, and many more. So you would see a different type of algorithm, and you can also find them online as well. The book only includes a few. So we want to know the difference between symmetric and asymmetric for our final exam, and also for general practice and security. Now, when you implement this in scripting, you would see that we would use the same exact key as defined in the program to encrypt, and then we would then refer to that same key to decrypt. So when you do the key generation, you would want to make sure that you duplicate the key for the symmetric encryption. Whereas the asymmetric or the PKI, you would have 2 separate keys. So you would have to generate the private key and the public key. The public key is then shared or sent for, so when we encrypt, we would use the public key, and the private key is kept as secret or private for the individual to decrypt. So in the scripting itself, we would see that the public key is then being sent or shared compared to the private key that will then be kept in secret or stored for the user. Any question regarding the definition for hash function, key hash function, and symmetric and asymmetric? And you probably have seen this in CIS27 and other security courses, right? In this week, we're going to apply this to Python programming. Here you can find on page 1 and page, or the beginning of page 1, the definitions and some example. Now, the majority of the chapter is going to address different Python modules that we can use for cryptography. One of the modules that we would see is the Pycryptodome. And this allows us to use cryptography at the low level. And in implementation of cryptography, we would want to implement modes, and we'll talk about different modes. So Pycryptodome is a preferred module in most cases because it's going to give you strong cryptography, and it also, you can implement hash functions and encryption algorithm. So some of the technology that we would see, or the algorithm that we would see would use Cryptodome. RSA is one, DSA is another. ECC, or elliptic curve, is almost equivalent to AES. It is very lightweight and it's good in performance. So to use this module, we would then implement the sub module that's incorporated. And it uses C routines. So as you know, most of the Python library is written in C. So in that case, we would need to have C compiler in order to build out the program. Now for the APIs, we want to make sure that we utilize the APIs for cryptography. And in some cases, you would have to declare or include the parameters accordingly, like initiation vectors, certain attributes that need to be included. So for the installation of Pycryptodome, we can simply do a pip3 install Pycryptodome, or you can also do the install build essential Python 3 dev first, and then be able to install the Pycryptodome. Let me see if I'm in this right now. Let's zoom in. You can also look up the documentation as so now I'm able to pull, right, the package for Pycryptodome. So it's already been installed successfully here. Okay. So we can simply use the pip3 if you already have Python. Now, in the package, you would find the submodule that would be referred to throughout the chapter, like Cipher, and other module in its class. So we would use a different mode in Cryptodome or Pycryptodome for various reasons. So if you use CBC, you have to include the vector IV as a third parameter. So these two modes require IV in the parameter, okay? CBC and CFE. We'll touch on the mode in a little bit. While the others would use only two parameters, or two in the argument you would have two, okay? Now, depending on the encryption that you're using, you would then specify the mode. So for example, if we're using PGP or OpenPGP, we would select the appropriate mode. And PGP, you often see that will be used for email and for various things here. So if we're looking at one of the algorithm, which is AES, AES uses block size. So you have to specify block size and key size parameter. And the whole point in using the key or key length is the longer the key, the stronger the encryption. So in that, we want to specify the size for the key. So for example, if you're using 512 or 1028, 128-bit key size, then you would then specify that inside the parameter. Another submodule that you will find in Pycryptodome is going to be crypto hash, and this is used to specifically for hash or hash type, such as SHA-1, MD5, SHA-256, and those are the hash type that it supports. As we know that there's flaw in MD5 and SHA-1, right? You can further implement SHA-256. So in using hash, you have to include the type of hash function that you want to implement, such as these, okay? And we'll take a look at some example. Now for AES, because AES is a block encryption, so two type of encryption in general, right? It either stream or it would block. So that means that it would chunk the data to separate blocks, and we can implement different type of modes for these blocks. So for example, Bitcoin, you would often hear blockchaining, and that's using CBC mode. And so that's simply apply exclusive OR operation, and it would chain from one block to another. So exclusive OR operation from the previous block would then chain to the next block as its cipher. Now, CBC is going to be slower than some of the other modes, and some modes are better than others, and some modes are more secure. So while blockchaining is somewhat secure, the performance of this is going to be slower. So each block of the ciphertext would then depends on the plain text that's processed from the previous or at that point. So in this one, for the CBC, you must initialize IV to make sure that the message is unique. Okay. Now, electronic codebook, this is traditional, and this is also an older legacy technology. It will also divide up into the block for your message, and each of them are encrypted separately using the same key. And the disadvantage of this is that when you have identical blocks, that would be identical to the ciphertext, so that can be guessed. So this mode is not recommended because it's not secure. Your counter mode or your GCM is very common as well. This uses 128-bit block cipher, and so the operation mode is in 128-bit. Its performance at the hardware acceleration enhancement for the processor with the newer processor, like your Intel and AMD now, that improves the performance using this particular mode. It also allows you to randomize your key, and so you can have randomization of key to improve two messages using the same key. So that way, because it's randomizing the key is harder to guess. So therefore, it is also a safe mode to use. So when you're using the Pycryptodome, especially for the AES, you can import in the CryptoCipher AES module. Because it is a package, you can specify which module you want to use, and you can implement the class and its object in your script. And so for the block level encryption in general, Pycryptodome is low level. It is able to accept 16-bit, 24-bit, 32, or I'm sorry, 16 bytes, 24 bytes, and 32-byte long keys. And so when you're looking at the keys, you can implement that for AES 128-bit, 196, and 256-bit blocks. So as you understand, the key length is different than the block length. So you can have different block size compared to the key, of course. So in this case, we can implement different sizes for the key length for various AES block size. So the idea is that the longer your key, the stronger is the encryption. Now, because it's block, keep in mind that it is some of the impact or the factor, your performance is going to be a factor. Okay. So compared to what you would see with stream-based encryption, it encrypt 1 bit at a time as it stream, and that's often fine. You will find that for web or when your data is unknown, right? The size of your data is unknown. So here gives you general description of your mode. So coming back to the questions, Number 3, and you don't have to put the verbatim from your notes. I just want to include that so that way we can see why it is the answer. So in number 3, when using AES, what mode is recommended for today's use? And we can use Cipher blockchaining or CBC, which is what you see now with the cryptocurrency. And it is peer-based. So with that, we can implement the communication and the hardware and the technology with that. Then the counter mode, which is an operation mode that is using 128-bit block. And with AES, initial or your IV must be initialized, right, in the parameter. So the attributes for IV must exist. So those are the 2 modes that we recommend for today's use for AES. And AES is very common in, smartphone communications, wireless communications. Wireless router uses AES, right? And so when it first came out, I think it was implemented in the smartphones, and it became really popular over time in wireless communication. So this is the recommended encryption algorithm for your router with WPA2. Any question? Okay. So let's come back to 4. Let's switch over to the notes first, and then we'll talk about the example here. So in example 1, for the script, this uses the submodule, which is crypto Cipher, right? And we would import AES. So you would define your key or initialize your key. And so your key must be 16, 24, or 32 bytes long. Okay. So your secret key. Then we create an object called Encrypt Aes. And we use this because this is C based. So it uses a constructor called new. And if you're familiar with C++ or C, so because we imported in AES, we now would create or construct an object, and we would use the encode method for the standard UTF-8. This is where you specify your mode. So in this one, we're using CBC, which is blockchain. And so here's our string for the third parameter. That was what was the chapter talks about, was you have to specify your IV. So we have to encode that with UTF-8 as well. Then now we would define our message. So you can put in your plain text here. And then we want to encode it with UTF-8. Now, depending on your approach, right? In this one, we would see the example with UTF-8 for AES, and we'll look at another example that uses ASCII for the encoding standard. So to encrypt, we simply create another cipher or another object called ciphertext, and we would use the encrypt method, and we would pass message as the argument. Then we will print it. So now at this point, when we print, it should show as a ciphertext. Okay, or it would be non-readable to the person who interfaced the application. For the decryption, similar to the encrypt up here, we would have a Decrypt Aes object, and then we would construct. So now we would then use the encoding for the key. So in here, we would also have 3 parts to our argument for your encoding for your key, your mode, and your IV. Then we would have an object called message decrypt, and similar to what you've seen previously, we would use the decrypt method. And here you want to pass ciphertext instead of plain text from what we've seen earlier, or message. So now we're going to decrypt the ciphertext. So we're going to pass ciphertext there. And then we can print out. So at this point, at the end, we would have a plain text message displayed. Okay, any question? Now, part of AES is to use password-based key derivation function 2. This is the later version of function 1. So this allows us to implement key generation for encryption and decryption. And so your book referred to PBKDF2, and that stands for password-based key derivation function 2. This allows us to also generate safe or secure passwords and iterations. So to make your password harder to when it's subjected to brute force, so we would elevate the difficulty level for brute force, we would use PBKDF2. That requires salting, so it would salt the passwords, right? That just bit stuffing. And the book says it's prevent, but I really think it just reduces the possibility of brute force. Okay. So it's going to do 1 salt per password. And that allows it to, it's basically lengthening the passwords, and it will be more difficult to brute force. It also requires a higher number of iterations to make the decryption process difficult to attack. So using PBKDF2 is beneficial. So in the next question for your assignment, we would refer to that technology. So for number 4, it asks you, when using AES, what technology prevents brute force attack against password-based key and reduce attack possibility? And that I meant for decryption. So we would use PBKDF2, which requires 1 salt per password, and also increase the number of iterations in keys. It reduced the possibility for brute forcing the password and decryption attacks. And we will take a look at the example on how that's being implemented in Python. Any questions? Let's come back to the notes first here. Oh. Okay, so we saw the encryption and the decryption with AES. Let me see. And these are the textbook example. So this is an example using PBKDF2. Let me pull this down a little bit so we can see. So similar to the last example that we saw on AES, you are going to import crypto Cipher. But in addition to that, when you implement in PBKDF2, you have to import protocol KDF. Okay. And then we are going to also import random from crypto. So this is the sub modules from crypto, of course. Just like the last one, we would then start with initializing the key. And because PBKDF2 require iterations, you have to also initialize the number of iterations. And here we use 10,000. We're using 16 byte for the key size. So you also need to declare your key size. And then we have an object called salt. And so here we are going to salt the password by using random with the new method. Okay. We would also have initialization vector, your IV. And this, we are going to use random.new and also read AES block size. Okay, so these are the objects that you are required to implement BBKDF2. And so for the parameter, we would then have the key, the salt, the key size, and the iterations. These are previously declared for your derived key. So unlike the other example, you have additional elements in this script that is required for salting passwords and also iterations. And that elevates the security in encryption or cryptography for AES. Then after that, we would then encrypt. Similar to the last one, right? We would have the parameter, your key, your mode, and your IV. So now your encrypted message will be stored here. Then we also declare your plain text, and we will encode it with UTF-8. So for your encryption for AES, then it's going to take this message and apply the encryption. So now your ciphertext is here. Okay. Then we will print the ciphertext. So at this point, it is unreadable. Now the decryption, similar to the encrypt, we would have an object called Decrypt Aes. And again, for our parameter, we would have the key, the rewrite key, the mode, and the IV. And we simply use the new method with that. And then your message decrypted, which stores the decrypted text. So we would then pass the ciphertext as the argument. Okay. And then we will print. So now, unlike the previous print, because when we encrypt, we would then encode. When we decrypt, we would decode. Okay. And in this one, when we print for the message, we would then strip. So this extended the program, but then because we are implementing the PBKDF2, which require additional elements for security reasons. So as you can see, the answer that we put down, we would see that in the Python. Any question? Okay, so now let's take a look at the example for DES. And DES is also block cipher. It is encrypting in multiple of 8. And so in example 2, you are again using the submodule crypto cipher. And we are going to encode using UTF-8. So what we have is we have the spaces for the user to input, and because it is every 8 characters, so you would have the 8. So the space would then include 4 additional white space that would represent your eight characters. And then the message, we would also encode UTF-8. Now here we hard code in our key, and your key is my cipher. So similar to the AES, you would see your cipher object here. We would have the key.encode and UTF-8 in our mode. So on this one, you only have 2 parameters. Okay, your encoding for your key encoded, and your mode. And so in this one, we're using ECD. And then we have 2 objects, your cipher user, which is going to be for encryption, and your cipher message, that's going to be for your message to be encrypted. Then we will print. So we would show now, at this point, we would have encrypted text. Now, once we have the encryption, we can now use it for decrypt. So here we have the cipher, right? So just like what we had before. To decipher, we have to have the user and the message. So we would do the decrypt and use the decrypt method for both. And then we can print out the plain text. But this one, similar to the AES, you have to decode. So when you encrypt, you would encode for the UTF-8. And when you decrypt, you would decode. And you would use the appropriate method accordingly. Okay. So when you execute this in terminal or command line, you would have Python 3, and then we can just call on the Python file. So you invoke, right, the execution for encryption and decryption from the Python file. And it would display this, okay, for the encryption, and then the cipher for the decryption. Any question? Now for RSA, because RSA is PKI or asymmetric key, you would use different keys to encrypt and decrypt. So let's take a look at example 3. So unlike the symmetric key encryption, when you're using PKI, you are using a different submodule. Okay, so here you are going to use a public key from Crypto. And again, we are going to also use Crypto Cipher, but on this, we're going to import in a different superclass. You will also require a hash, so you have to do crypto hash. And here we're using SHA-256. And then on this one, we're also going to do digital signature. So we are going to import in crypto digital signature. So the initial part in any encryption is to generate the key. As previous, you saw that we actually declare our key. Here, we're going to have a function called generate. And we're going to declare our keys. Our key is going to be generated for RSA. So it's going to be bit size. And we're going to return key from that function or method. We have another method called encrypt. And we're going to, because we're using public key for encryption, in your parameter, you have to put your public key and your data, which is going to be defined. And for the encryption for the Cipher object, we're going to use the PKCS1. This is going to allow us to construct or create your public key. And we're going to return encrypt data. So we're going to return the encryption for your data there. The third method or function, we're going to use private key to decrypt. So here in the argument, you're going to pass the private key in your data. And again, we're going to use this to declare our cipher, which uses the argument private key. Okay. And we're going to return the decrypted data. Earlier in the concept or the lecture, we talked about the key length. So here is where your key length is going to go for RSA 2048. So it's going to generate 2048-bit key length. Okay. And so when we print, we're going to print your public key information. And we're going to export it because we have to exchange public key where the private key is going to read. So with that, we're going to generate a file that's going to hold your public key values. Okay. Now in this program, we're printing private key, but it's going to be a .pen file. So if you ever use PuTTY or, some type of terminal interface type of applications, right? It generates when you have to generate the key and it generates a .pen file. And you would use that file, right, in order to establish authentication because that's part of your private key. So now we're going to export, right, your private key in PEM. And this is how you would create a PEM file. So when you look at PuTTY, right, that part, when you click the drop down arrow and you click generate key, right, it automates this process right here. So we simply create a file for our private key. Then for the next part, we have text to cipher. This is the object to encode UTF-8. We have hasher. This is how we're going to generate the SHA-256 hash. This is for the digital signature. So for your signer, you would then pass the hash to sign because it required the hash value to sign for digital signature. Then in the next section, we have a verifier object. This is going to be for the keys. It's going to verify your hash for your signature. And once it double check that, right, because it needs to match the hash. And so once it matches the hash, then it's valid and it's going to allow you to digitally sign. Otherwise, if it doesn't meet that condition, it's going to show that the message was signed with the wrong private key if it was modified. So in the case where the private key is jeopardized, right, it would show that. And so for the next part, we just simply have encrypted data. We're going to print our encrypted data, and then the decrypted data, we're going to print the decryption. Any question? Okay, so here I added a couple of notes regarding your methods that you would use, your public key and your decode, the .pen, which is your text-based encoding type. And that was what we generated from earlier on when you saw how PEM can be generated for the private key. Any question regarding PKI? So another module that you can use for cryptography is cryptography, right? We've seen this in the advanced Python class. We've seen this throughout this class a little bit. So this allows you to do high and low level for cryptography, and then you can implement different algorithms for symmetric, message digest, and key derivation functions. So you can simply do a pip install or pip3 install cryptography, and I can show you that should be accepted here. Okay, I've done this in the prior. I think we did this part of one of our labs as well. So you can see that it's already been installed, but you can do just a pip3 install cryptography. The benefit of this is that it's going to give you great performance for encryption operations, and you can also implement fernet. Okay, so this is a package that's for symmetric encryption. Oh, I keep having typo everywhere. Okay, and it also assures that the keys are not manipulated or modified. And so when we look at example 4, we can import in the submodule for fernet, and then we would then create our key object. So construct our key object here. And again, we also have a Cipher suite that's going to be your fernet key. Remember that symmetric encryption uses the same key to encrypt and decrypt. So similar to the prior example, you saw that we have to do the encoding for your message. Now you are going to use the Cipher suite to encrypt the message. And then for your Cipher suite, you're also going to use that to decrypt. Okay, so Cipher suite allows you to have the same key that's used to encrypt and decrypt. Even though you generate the key here, this brings it to see how Cipher suite is in use for encrypt and Cipher suite is used for decrypt. And then when we print, we would then decode that. So your ciphertext is going to be decoded. And then when we print for our decrypted text, your plain text is also going to be decoded, as earlier we encoded. Okay. So it can be simply implemented for symmetric key using fernet. Any question? Okay. So here I highlight some of the methods that we use in that program. Sorry, I was typing and I should have double checked it, but there you go. I'll re-upload the document with the correction. Let's re-highlight these. Okay, so there are additional examples on how you can implement PPK DF2 submodule, right, with fernet. So this is an example that you can implement password-based. Okay, it uses the fernet and then also additional submodule like hazmat and so on. Now, because we're using PBKDF2, you have to do the salting of your password, and this one is going to be 16 bytes. And so we also need to implement the iterations like what you've seen before. So either you declare or you can put that into the parameter like this. And then we're going to have the derived key for your password. Then we're going to use it to verify. So when you implement this, you would see that it would elevate the security, but then again, you have to implement the hashes, the salt, the iterations, and so on. Okay. Then after that, after you set up your PBKDF2 components, then you're going to have the key for the fernet. This is where you would decrypt and encrypt. Okay. It's not too long. I think it can simply be implemented, you know, if you want to elevate the security for that. There's also example on how you can use this with AES. Very similar to the last example. Okay. But on this one, we can use it with, we can set up the token and be able to use that for to decrypt. But AES also, we can use PBKDF2 with AES. So there are ways, variations in how you can implement this in Python in different algorithms for symmetric encryption. And we saw asymmetric encryption using PKI, right? For public key, setting up public and private key. So those are the example for encryption. I think I put down most of the ones that were highlighted and also explained in the text. The second part of the chapter talks about steganography. So this is where we can hide text and data in images and files. And similar to what you've seen with encryption, this would also require keys. So you have the secret key, the public key. We can also put data in images using least significant bit or your LSB. So that just means that every least significant bit, the most right-hand side bit in a byte, because there are 8 bits, so the right-hand sided bit is changed to a binary value. Okay, that would represent the file. So we can hide a file without causing a major change to the actual content or image. So if you have a file that's 1008 bytes, which is 4.08 kilobytes, we can hide a total of 4008 bits, because every byte you can put in a bit at the least significant bit from most right-hand side. You can also hide things in audio. And so it would do 16-bit files that would be for 216 sound level. And some sound we cannot hear. You can also put in video. Video, the benefit of this is that you can put in large data in the video, or if you want to use video for steganography. And then you can simply put data in text type of file. So all that is just going to process data compression. Okay, because usually it's text to text. So in the next few questions, we can answer this, right? Number 5, what is steganography? What's the advantage of video steganography? So steganography is an art of hiding information in text, image, and other form of digital documents or file. Video steganography can contain large data, larger than what you see in images and text. As we talked about LSB, your least significant bit technique. So if you have 4.12 kilobytes as a file, so 4.12 kilobytes is going to be 4,012 bytes. That means that we can have 4,012 bits hidden in 4.12 kilobytes file. Using LSB, that is. Because for every byte, you can have 1 bit with LSB, the least significant bit. So that means that 4,012 bits can be hidden. Any question? Just a few more to go. So we'll touch on steganography and finish that up, and then we'll go into key generation, and that will wrap up chapter 14. Okay. So coming back here, this is the example that you can refer to answer that question about LSB. So this is the example for steganography with LSB. Let me double check it real quick. Yeah, same. Okay. So you are going to import in, because we are using image, so you have to import in pill. Okay. And then again, going back to the last chapter when we talked about pill, we have to install Pillow on Linux or Mac. So the first method here is we're going to set the least significant bit value. So the parameter of that is going to be value in bit. If it is 0, then you would take that 0 and you're going to AND it with 254. As 254 represent the decimal value of a byte. Otherwise, else, your value is going to be OR with 1. So anytime that you AND it with the 0, right, you are going to get a 0 as an output. So if it is a 0, we would take the 0 and AND it with this. We would have a 0. But, you know, with the OR, anytime that you have a 1 in an OR, it's going to output as a 1. So if I have a 1 here, I OR it with a 1, I have a 1. Okay, so it's going to return the value there. So this is how you would set the least significant bit. Then once you do that, you're going to have another method called get LSB. And so here we would declare the if statement. If value AND with 1 is a 0, then we're going to return a 0. So if my value is 0, then if I AND it with a 1, I get a 0, then it's going to return a 0. Else, it's going to return a 1. Now, the next part is going to be for the image. So we are going to have a third method called getPixelPair. And we're going to iterate. Then we're going to return, right, the compression of what is defined as A. So it's going to pair up the pixel. Then after that, there is a method called extract message. So you declare an object called cImage, and this is to open your image. Because your pixel is a group, so we want to put that into a list. And so we are going to pass cImage here with getData method. So it's going to put it into the container, and it's going to iterate through that container to find your message. Then we have a for loop. So we're going to pair, right, pixel 1 with 2. And for your message byte, it's going to start with OB. So now, because earlier we have get and set, so we set LSB and then we would get LSB. So here we're going to use that because for every pixel or every byte in that image file, we are going to have 1 bit that is going to be hidden. So we need to pair the pixel, and then we need to process the hidden bit. So we have pix1 and pix2, right? For the pair, we're going to process the hidden bit. And if your message byte is going to be this, it's going to break. It's going to move on to the next one. Okay. So this is how we would be able to extract your message. And now we are going to hide the message. Similar to how you extract, but on this one, you open the image, you have to convert it to RGBA. Okay. And you're going to have a construct. So you're going to construct the image. And similar to the last time when we talked about extract data, you have a container. And so your image is going to have a dimension. So it's going to be width and height. So this is going to give it a size. Then in your container, you are going to use getData, and you're going to put that into the new array. And also use your pixel pair. So we have to set up where we can access the pixel pair to be able to hide your bit. And that is where we would use the for loop. So to access it, and then we would append, right, your hidden bit. So we're going to set it for pixel 1 and pixel 2. Then we're going to output your new data into a new array, save it into a file, return the file or your out file. Then we want to confirm to the person who interfaced the script or the application, right? Showing different stages for plain text. So here is where we will call your method. So on this one, you can see that extracting and hiding message into a message is a little bit more complex, right? As you have to pair up your pixel and then set that into a container and be able to access that. Okay, so that would be the example 7 from the notes. Now there's a tool called Stegano, and this is used to hide text in a PNG file. You can also use it to find hidden message from the image file. You can also use it to hide image inside an image. And you can simply install it using pip. Okay. I went to the documentation for this. Your book didn't really touch much on the example for Stegano. I put the link here if you wanted to take a look at their resource and example. I think I have it open. So let me move this down real quick. So if you access that link, you will find their project information. And then you can also look at the, the documentation and the homepage links here. Okay. So it walks you through how to install Stegano. And then if you want to use the tutorial page, you can click on this. But they show you some brief example there. Okay. My internet is a little slow, or the page is slow to load. So this is what I've gotten from, this is where your example from the notes came from. Okay, so we can take a look at that a little bit. Okay, so we are going to use LSV with Stegano. So here you are going to import in LSV from Stegano. And compare this to the last example that you saw. Using this tool simplify your script quite a bit, right? Because it is an image file, you simply just use a module or a library to process that. So you don't have to do a lot of pixel pair and all of these other things. So you can just use this tool to be able to but especially with the PNG image. Okay, so what we're doing here is we are going to hide this message or the text in this picture, which is a PNG file. So after we import in the module, we would then declare our secret, and we would use the hide method. This is just the destination file or the image file. So if you put the image file in the same folder or directory as your script, you don't have to put the path. So this simply is the path where it will find your image file, right? So in your parameter for your argument, you need to just put your PNG file and what message you need to hide. Then we would use a save method to save it into the image file. So it's going to take this and put it in there. And then for the next object, for our clear message, we would then use the reveal method to show what's hidden in that image file. And then to run it on the command line level on the CLI, you can just use Stegano LSV like this to hide and to reveal. But for script, it would be like this. So compare these 4 lines to the prior examples. You can see it does simplify our script quite a bit. Okay. Then we have another module called Steppik. And this would be a module and a CLI. And all of these, you would see that they use LSV, so least significant bit technique. So you can hide data and images. And similarly, you would see that it would use encoding and decoding, or encode and decode method. So in example 9, okay, using Steppik, you import in Steppik, and then again, we're going to use pill for image. You're going to open the image, and assuming that this is in the same directory as your script. So here we would have the Python PNG. Again, as we talked about just now, we're going to encode, and we're going to use UTF-8. Then we're going to save it. So similar to what you've seen with Stegano, we're going to use the save method, and we're going to save it back to the file. Now, if we want to decode it or to reveal, we would then use, again, go back and open up the file, which is Python secret PNG, and then we're going to do the decode. So again, compare this to earlier, right? Using LSB without any kind of module or tool for steganography, it is tremendously shorter using the tool or the module. Okay. Any question? So for 7, we can say Stegano is the tool that would be used for PNG, but you can also use Steppik module. Now it tells you to refer to example 8. You can simply write a Python script that would hide secret message in a PNG file. Let me see if I have a code example for number 8, and you can simply screenshot your code or copy and paste it below. This. So for number 8, right, if you refer to that example, I would start with from Stegano import LSB. I would declare my secret object, and we're going to hide. So we are going to do lsb.hide, and assuming that this file is in the same directory, and make sure that is the exact file name. So you can just have a PNG file. And then the message or the text that I want to hide. So secret message. Now I can save it over, or I can save it as a different file. So if I decide to save it as a different file, right, when I reveal it, I got to make sure that it is that same file. So after I hide this text message, I would save it as this file. And then I wanted to do a print confirmation. So I just put message hidden. And to reveal, we would then have an object called clear message. And we would use lsb.reveal method. And we would process the file that we just saved that contains the secret message. So image1 secret PNG. And then I want a confirmation that it is revealed. Okay. So without the print, we can simply do this in 4 lines. And you can do more, right? You can do print clear message. So I will print And we can say clear message like that, and it should print out this. Any question? And this is for number 8. And you can also use the notes as example. If you want to look at, you know, the source code for it, I think it's also on GitHub as well. Along with, you know, you click the link through their documentation page, you will find. Okay, any question? Okay, so for the next part, we're going to talk about key generation. And for Python, there are 2 modules that we can use to generate keys, randomizing keys at least, secrets and hashlib. I think earlier on in the semester, we lightly touched on this. Now we're going to come back to it, right? So secret module allows you to generate encryption key using random numbers. This will be suitable for passwords, user authentication, security tokens, and other areas. Now, when we say random, it would also, in this particular module, we will refer to pseudo-random. That means that it looks randomized, but truly not, because we're not implementing anything from our environment or any factor that would give it different seed. So for example 10, we are going to import in secrets. And we are going to import in ASCII letters, uppercase, and digits. This is to generate a password that will be secure. So now we have a container call or an object called characters or container. We would have ASCII letters, uppercase, and digits. We're going to go all the way up to 16 characters for the length. So what's going to do is going to generate individual characters, and it's going to combine it to give you a strong password that is this length. So if you want to automate password generation, even for one-time use, you can do it this way. Okay. Then we would print out our randomized password. So that's how you can use secret module to create random passwords. There's also another example in the text where it would generate keys for a URL. So we import in secrets, we import in string. We have a method called generate secure URL, and inside that, similar to the last example, we would have a container that's going to store ASCII letters, digits, and punctuation. Unlike the last one, we're not using uppercase. We're using letters, digits, and also symbols or punctuation. We're going to use the choice method for the lowercase, the uppercase, the digits, and the punctuation. So it's going to also update that as it goes through. Then we're going to loop through it. So up to 16 characters. And we're going to generate the password. And then for your URL, this is your target URL. This is going to be your domain. What it's going to do is going to use this password, right, and generate a secure token and pass that token to the domain. Okay, that will be here when it calls for the method. Any question? Okay, last but not least, we're going to talk about hashlib. So this allows us to obtain hash for password or make or elevate the security for hash. So you would import in hashlib. In example 12, you ask the user to enter their password. You would take that password, and here we're going to use a SHA-512. So we simply use a SHA-512 method to generate the hash for the password that the user entered. Then we're going to print the hash values and the hex digest. Okay, so that can be easily done in a few lines. And as you know, I know most OSs, it has this mechanism built in for, the hash functions that it supports, like MD5, SHA-1, 256. But if you want to implement like different hash function there, you can, or hash algorithm, you can use the library that supports it, like hashlib. Another example that you would see is how it's used for salt. Earlier, we saw how this is used with the PBK, right? So here we can use hashlib, and then you also have UID. We define a method to hash the password. So you would then set up the salt, because here our objective is to salt the password. So this is where your UID is used. And so to generate the hash, we would use a SHA-256, and then we would do the encoding for the salt, the password encoding, and hex digest plus salt. Then to verify, we would have a function or a method called check password, and it's going to look at the hash password and the user password. So pass those as arguments. We have to split the salt now because it was combined earlier. We're going to return the encoding of your password and salt. Then we have a second input, enter your password. This is going to be stored in new pass. It's going to hash the new password. Then we're going to print the hash. For our old pass, it's going to store the password that you want to verify. So we have the user input that again, and we want to compare. So what that does is it's going to generate two hashes, and then it's going to compare if they match. Okay, and that's how we can double check to see if the password is going to be a match or not. So for the web interface, you often see this, right? For authentication, for generating new passwords, and so on. because it would ask for your old password in order to generate a new password in some cases for some web app. You can also use hashlib to hash a file. So import in hashlib, we ask the user to enter the file name. We're going to open up that file. We're going to encode it using UTF-8. And then we can also print out information, but here it just stored that. So it's going to read the data. We can use it to test algorithm. So import in hashlib, we're going to loop through. We're going to print out the algorithm. We're going to we use new method, and we pass the algorithm. We have now our password is going to be encoded. We're going to check. So try and accept here allows you to check your hash keys or your hash values. And then print. So for number 9, the modules that we use to generate keys, we can use secrets, and hashlibs is for hashes. So I should just keep secrets. I think it's correcting, so there we go. So for 10, refer to example 12 in unit 14. Write Python script that generate password hash. So when we come back to 12, you can use example 12, which is this one, right? That's pretty simple. So you can use this. Now, you don't have to ask the user to input. You can hard code in your password as a string, and then process that with the encode, and then print out your hash for your password. Let me see if I have that. Okay. Any question? So this wraps up all 14 chapters. This is chapter 14. Some content of this will show up on the final. I'll put together a small lab for you this week so you can apply encryption in case you need to do that for your career or whatever that is. Okay. Or competition and so on. But I will also have your final review document be available this week, so you can take a look at it. What I plan to do is I will go over it next Monday. It won't be an assignment. I will just go over the questions and you can use it as a study guide. Final exam will be open during the finals week, and it's multiple choice, so there will be parts of it that will have script, and so you will have to be able to understand what that script does. Okay, so it's going to go from unit 1 to unit 14. Oh yeah, that's right. You know what, I might just record it for you and I'll put it on or we can meet on Wednesday, but that's really close to the final exam. So thank you for reminding me of the holidays. So no class next week. But if anything, I will put up a video or I will send out an announcement. Okay. Okay, so make sure that if you finish with this assignment, make sure that we put up our assignment for submission, and then I'll get your grade process this week. And so before you enter the final exam, you would have everything but the project and the final. Okay. And the extra credit, of course. All right, any question? Okay, so let me stop share.